y hat, you can do something known as a dot product or an inner product, right? The product of y, an inner product in general, like if you want to do a dot product, just perform y transpose multiplied by y hat. This is the same as this, right? And this is the same as this, all right? And it's a summation because you're multiplying corresponding elements together and then summing them together. So it is a summation. So this vector form looks like a shorthand notation for this, but the implications of writing it like this algorithmically is wonderful, because rather than performing this, you know, if this was a very large matrix, large vector, for example, let's say with like millions of parameters, performing that computation is going to take a lot of time. But if you save it as matrices, then that computation takes a much shorter time. It essentially, it helps you to take advantage of the underlying data structures that exist in our programming languages, right? So phi j of x, so let's look at examples of basis functions. So this is an example of basis function where we're saying phi j of x can be simply the element xj. So it is completely linear. It is both linear in the parameters, but also linear in the inputs, because the inputs x naught all the way to xm, all of them are simply scalars. All right. So this is under multiple linear regression, where we are simply saying that your function f of x is linear in the sense that it's w naught times x to the 0 plus w2 x to power 1, rather w2 x2 plus w3 x3. It's fully linear. The x's are not raised to any power. So that's an example of a basis function. Another one is the Gaussian basis function. Gaussian from Gaussian distribution. So it simply means phi j of x will be exponential x minus mu j, which is the mean, divided by 2s squared, s being the variance in this case. Right? So this is a Gaussian basis function. And there are many other basis functions. I have mentioned that there are sinusoidal basis functions. Polynomial is an example of a basis function. But what is the underlying, what is the common denominator in all these basis functions? They help us to create linear functions where the output is linear in the parameter. Okay. I just want to discuss something briefly known as the design matrix. Building on top of this basis function phi. Right? So we want to create a design matrix, and it's going to be convenient. And basically, what we need to do is to create the design matrix. All we need to do is to stack all the samples together. The first columns are always ones. I think you will see this for the in a moment. And what it's going to do is it's going to help us to make a compact prediction for the entire data set. Let me. I guess it's not. I have not included here in the slides, but let me just write it down. Where was that thing you used to? Okay. Can you guys all see the board? Hopefully. So we can create, let me just put it like this. Sometimes you need to refer to your notes so that you don't write. Yeah. So yeah, you're going to have basically the first column 0, 1, 2, all the way to m. Okay, and then you can write phi naught of x1, phi naught of x2, and you go all the way to phi naught of xn. So basically, remember from what we had discussed earlier that your rows are always your samples. So this is the first sample, second sample, all the way to the nth sample. So these here are samples. Essentially, what you're doing is taking your data matrix and passing it through the basis functions. Okay, so your basis function might be the polynomial, but it might also be the linear basis function, which is that phi j of x is also the same as xj. It's completely linear. Then you have phi 1 of, of, make sure I'm getting it right. Phi 1 of x2, phi 2 of x. Okay, this phi 1 x xn, I guess. So all this is going to be some phi of xn. So this is going to be phi m x1 phi m of xn. So essentially, we initially we had our data matrix, which was x1, x2, all the way to this was our data matrix all the way to xn. Then you take this and pass it through the basis function phi. Then you end up with a design matrix that looks like this, where each element has essentially been taken through the design matrix. And what that does is it helps us to write this in a very compact way, as saying that now our prediction y hat is the same as phi multiplied by w. Right? So phi is a matrix, and w here is a vector. And we need to keep that in mind, because the matrix, this here that we are referring to as the design matrix, is a matrix of size not m, but n by m, where n is the number of samples and m is basically should be the number of features, like that. So it's n by m, and your w there is this is phi, and the w, this is a matrix, and w is a vector. It's a vector, it's a column vector. This is m by 1, right? So you take a matrix of size n by m and perform a product with a vector of size m by 1. What is going to be the result? It's going to be the result is these two are compatible, so you end up with n by 1. N was the number of samples, all right? So basically you end up with an output of size n, telling you it's exactly, you've made a prediction for each and every one of the samples. Okay. So essentially, this product here is saying, instead of writing that summation that we had before, the summation that we had before, instead of writing this summation like this, okay, you can write it as a matrix vector product, like that. Okay, you can write it as a matrix vector product, and so that changes how we approach our problem, because it is no longer a summation that we have to perform a for loop. It is a matrix. Optimize, perform an optimization of the linear programming. As in a sense, I'm saying you may not even have to use the gradient descent algorithm. You might perform an analytical solution and get the solution for your linear programming problem. Anyway, let me discuss this briefly. Probabilistic framework. So we've said that our data generally is coming out of a problem. It's coming out of a process. Y is equals to this matrix vector product, WT multiplied by phi of x plus E, epsilon rather, which we said is irreducible noise that you cannot do away with. This noise is assumed to be Gaussian. You guys understand what I mean by Gaussian. It's normally distributed, the bell curve, right, which is centered at 0. Okay. Then we define some term that we are referring to as the inverse of variance. Now it's Gaussian noise centered at 0, but the Gaussian always has a variance that we represent as sigma squared. When we perform the inverse of that sigma squared, we get a term that we are referring to as beta. We'll call it precision. Okay. When the beta is high, that means I guess it's just easy when I draw these things. Okay. So with a Gaussian distribution, this is the mean, mu is equals to 0. That is the center of the distribution. With normal distribution or a Gaussian distribution, the sigma squared, which is the variance, tells you how spread the distribution is. Okay? So if the variance is very high, you will have a distribution that looks very wide like that. And if the variance is low, you will have a distribution where super sharp, really sharp like that. It is this property of the variance. It tells you how spread the distribution is, how close the values generally in your data set are to the mean. Okay. So when we say that high beta means the noise is tiny, we simply mean the distribution is very thin. Why? Because a high beta also means that the sigma squared is very large. Am I confusing this? High beta means the sigma squared is very low. So it's a very sharp distribution. The gentleman who was discussing statistics, you can learn terms like kurtosis and stuff like that. It tells you how sharp your distribution is. Okay, yeah. This is what happens when you generate your notes using AI. Yeah, but yeah, I guess. But I guess you really don't need me to include that in this visualization is enough. Okay. So what I want to discuss now is something called maximum likelihood intuition. Just to understand, when you draw a curve for your prediction, what exactly does it mean? All right. Okay. At this point, I think it's just better to so let's say, for example, that you've done some kind of fitting. You have some data, and you've drawn your curve, and you realize your curve is like that. Okay, it's your best fit. Okay, maybe the data points was somewhere like that, like that, like that. And then you drew your fit, you did your optimization, and that becomes your graph. This is Y, and this is X. Okay, this graph here, this fit here that we are calling as the line of best fit. Okay, it tells us that when for a point here, let's say x1, this is the value according to your graph, according to the fit that you did. In reality, when you fitted your curve and you realize that it is there, in reality, what we are simply saying is that this value here, let's call it y0, that value there is really the mean of a certain cluster of points that are possible. Are we getting the point? That we can take that normal distribution curve here, and we can in a sense we can in a sense draw it here and say at each point along this curve, there is a normal distribution curve that we can draw. There's a normal distribution curve that we can draw. And this point that was predicted is simply the mean. It is because remember we say this data set has some Gaussian noise that is within it. So when it has Gaussian noise, we are saying this point, there is a number of values that it is possible it can take. Some values are highly probable, some values are not very probable. If, for example, we were to make a prediction and say this line is supposed to have passed here, just following how our curves looks like, we can say this point is highly unlikely because it is away from the center of the distribution. The points that are near the center of the distributions are the points that are highly likely. Points that are away from the center of distribution are highly unlikely. Okay, so this highly unlikely thing that I'm talking about is what we are referring to as the total likelihood. Okay, so basically for every single point x1, there are an infinite number of values of y that are possible. There is a y1 that is possible, there is a y2 that is possible, and maybe there is a yn that is possible, all these values. The likelihood, the total likelihood of any of these points is the same as saying, taking the probability of y1, maybe y1 is here, taking the probability of y2, maybe it is here, taking the probability of yn, maybe it is here. Perform a summation of all of them. Okay? I guess, understanding some of these things maybe also require a bit of exposure. But let me just say that in case you are not able to master this during the lesson, don't feel that it's impossible for you to understand linear regression. Okay? But when we are doing this summation of these products, or rather, this is, you perform the probabilities of each of these points and then perform the products together. All right? But performing a summation is always better than doing a product. So what we then do is take that, all those probabilities together and say, let's perform the log likelihood, the logarithms of each of these probabilities, and then convert them to a summation instead. It's much more convenient that way. And then we take that maximum, we take the log likelihood and perform some kind of, differentiation, some calculus, and then we maximize that value by equating it to 0, and then we minimize that, and it really ends up being a summation of square differences. Let me just... So this is what you're seeing there. This is what I was talking about. That when you take x naught, there are an infinite number of possibilities that the corresponding value of y can take. Because we can draw a normal distribution curve there, and we can say along this line, all these values are possible, except that the one that is most likely, it's the one that is at the center of the distribution, this value here. It is at the point where the mean is 0. The mean of the Gaussian noise at that point is 0. Because that point also is affected by the noise. Now, I don't know how useful this is going to be, but let me cover it anyway. Okay, so given the parameters that our model takes, and this model is a linear regression model, the probability of a given point y, probability of y. Hopefully you understand this notation, probability of point y given. That given these parameters, given the inputs that the model has, the parameters w and beta, which we were referring to as our precision. Given these points, the probability of a given value y, the probability of a given value y is normally distributed. The probabilities are normally distributed, like we had seen in the curve there. It is a normal distribution. It is a normal distribution where, I don't know whether you've seen the normal distribution written something like that. It is normally distributed with a mean mu and a variance sigma squared. So in this case, really, that point, the point y, this predicted point y of x naught and w, that point is the mean. It is the mean of possible values that point can actually take there. And the variance is beta inverse. So the point is y given w, the point is y given wt phi of x, and the variance is beta inverse. The beta is the value that we were referring to as precision. So then after that, we're saying the total likelihood is simply the product of the probability of each point. Some points being highly likely and some others being very, very, very unlikely. Okay, so I just don't think it's important for me to spend all the time, deriving all this math here. But basically, we're saying we can take that log likelihood by taking the value. Others are not. For instance, when we expand this summation over here, we realize that beta over 2 pi, which is inside the summation, is independent of w. And even inside the summation as well, this exponential it's going to be, exponential of x minus mu over 2 times the sigma squared. Right? And so what we end up here is that we can expand this by taking the logarithm, and we can remove these two values from the summation, being beta, or the logarithm of beta, not dependent on w. Mean of 2 pi, that's a constant not dependent on w. Our objective is to maximize that value, is to find parameters of the model. The parameters of the model are the w's, the w vector. We want to find the parameters of the model that maximize this value. Right? So we are to maximize the value. We have to do some bit of calculus. We have to differentiate, for example, with respect to w, and that's where we are interested in the values that are dependent on w. Because if we do a derivative of this equation with respect to w, we realize that this reduces to 0, this reduces to 0, but this is non-zero because it is dependent on this basically dependent on y. But here is something else. What you realize here is that inside this summation here is literally the sum of square differences that we had come across earlier. Why? Because the value yi is the predicted value of the model. And then this vector product wt multiplied by phi of x time.
Rather, this is actually the predicted value, this is the actual value. So we are doing a sum of square differences. Actual value minus the predicted value. In any case, really, it makes no difference. So at the end of the day, we are squaring the value, which means any negatives are going to vanish or disappear, essentially. So it's interesting that by looking at log likelihood itself, we still end up with the same similar value of the sum of. Right. So yeah, sum of squares is a function P of W that we have come across now in our previous class. So we are interested in this function because we take this function and we perform optimization on it with respect to WT. What we will end up with is the optimal location. The location that minimizes the maximizes the log likelihood, but it also minimizes the error. Yeah, these notes are available in the when you go to the page, it has notes. I can share you the rest of the notes as well. It's something that was key because I don't know what's important. Okay, so I want to talk about this question. We see that for our difference yi, sum of square differences, the differences between yi and phi, that two transpose multiplied by phi, and we are squaring that. And the formula is I this is like predicted value, or rather actual value, and this is the predicted. I did say I presented this as a table and say, no. These are simply two vectors. This is yi and W transpose yi. There is a value here, there's a value here, there's a value here, there's a value here, there's a value there, there's a value there, there's a value there. Now, there's a shorthand way to write these differences. You can represent this as phi w minus y, then take the transpose of that, then phi w minus y. It's essentially the same thing. Like say, you have two vectors from these two. You have these two vectors, and you have these two vectors. If you want to find the dot product of the two vectors, all you need to do is transform one into transform one of the vectors into a row vector by transpose. So this transpose that you see there is what it's doing here by performing that transpose. You get a row vector. And then a column vector. And then you can go a vector where you multiply the first and the first. And then the second element multiplied by the second element until you get to the end and sum all of them together. This is exactly what we're doing here. Except that the products in which the values which we are dealing with are actually different. It is this difference here. This one minus this. This one minus this, this one minus this, is giving us the value that is right. And the reason why I'm belaboring the point to this idea of writing this as vectors because it simplifies our operation. and will help us get to a point where we do not have to perform any grade unless it is necessary. Instead, we can solve this equation. We can minimize this equation by simply performing an analytical solution using the properties of matrices. Okay. Then, once we do that, so we move from the point where we had a summation to the point where now with this, we can apply certain rules of multivariate calculus and certain rules of multivariate calculus, and then set the gradient to zero. Okay? Again, not captured in my slides, but I guess I will show you in the notes. Okay? But we initially begin with this value, phi w minus I. Then take the transpose multiplied by phi w. Then we perform a differentiation of this. Differentiate this function. It looks difficult, but this is nothing but multivariate calculus. And maybe there should not be given short term to not differentiate a function in multivariate calculus. But really, if you have a function, you want to differentiate a certain function in this yes, I don't think it's so clear. Let me write it. That basically you have if you have a function that transpose A W, where A here is a matrix, right? And you want to differentiate this, you represent it as a function. It's a function really very close to what we interested in. How you value this. That the answer is going to be 2A. And you're going to differentiate B value of W transpose B, and the value is going to be B. Just noting those two short rules. Then take note of the fact that there's an app here. So when you differentiate that transpose phi W, when you differentiate that, all you need to realize is that this phi W, this phi transpose phi can be taken as an integral matrix. Take it as an integral matrix, like our A in this case. So in this case, the value, the result there is going to be 2 phi transpose phi W, and then multiply by the half, and what you end up with is phi transpose phi. Taking that phi transpose phi as a single individual. And then the other one we have is 2W transpose phi transpose Y. It's similar to this one over here. That transpose phi transpose Y differentiate with respect to W and the left phi transpose sorry. So in this case we have B. So that means the only thing that we need there is phi transpose. W here is so then the end result is going to be, and of course, this third term, Y transpose Y disappears. Y disappears because it is not a functional. It's not a functional term. So you partially differentiate that the same term vanishes. So you learn this here. If you can solve this equation here, when you are doing the differentiation with the percentage of this W, that is the analytical approach to doing optimization. So if we can solve this equation here, then we are looking at an analytical solution to the linear equation. So to solve that equation, all we need to do is notice that this is a derivative. So all we need to do is equation 2. That's what we are doing here. Phi transpose phi W minus phi transpose Y. Okay. It's really known as the normal equation. Come across it about the optimization. Okay, so you end up with this phi transpose phi this phi transpose y. What are we interested in? This is an optimization problem. We are looking for the parameters that maximize our metric or minimize the loss or minimize the error. So we are solving for W. In fact, as far as you can, when you look at that equation, the only thing you're missing is W. You have phi, because phi is a basis function. Or rather, not a basis function, but your design matrix of basis function, you already have it. You have y, because y, and you have values. The only thing that is missing is that. How do you solve that? This is a normal matrix equation. It's like ax is equals to. When you have ax is equals to b as a matrix that you're looking for x, what do? You multiply both sides by the inverse of a. That's exactly what is being done here. You multiply both sides by. When you multiply this left hand, let me put it this way, you multiply this left hand side by phi transpose phi inverse. That means phi transpose phi inverse multiplied by phi transpose phi. You get an identity matrix. So in a sense, you only left with W on the left hand side. Then on the right hand side, you also multiply phi transpose T, phi transpose Y by phi transpose phi inverse. And we end up with this value over here, which we are referring to as the ordinary least square solution to the linear programming problem. This value over here. So you began with the design matrix, but in the end, you have ended up with so you began with phi. You began with 1. And you ended up with the solution. That means the parameters, these are the optimal parameters. Okay? So we are calling this as the ordinary least square solution. Because what we are calling there is ordinary least square. Equals to phi transpose phi inverse multiplied by phi transpose. Why? Okay. You know each of these values, you know times. And by the way, we see that phi x really for a simple linear programming problem, this is what the x value, which means if you have these basics, if you have these design matrices, this you have everything you have here. What you need to do is perform this computation. This is a matrix product. It's a matrix product. It's simple. No unit writing code single. Have inputs for that into a matrix. Then you can perform this computation. Now the solution. Linear equation problem. Now, for those of you who work with linear equation tools, say, for example, when you perform that function, when you say your fit x like that, and your solution comes instantly, what you don't know as happening in is that number is this equation. That is exactly what number is doing. That's why we perform this is short term. But okay, hopefully you understand. There is a name to this equation. This value here, phi transpose y. That is probably known as the Matrices because it's not really the rest of the information. Just so that you can clear the okay, that's what you need to do. But it doesn't always work. We don't always say. Now, and the reason why it's not always what we do that is I want to look at this phi transpose phi. Phi transpose What was the dimensionality of the matrix? Was 5 with an n by n matrix, where n is the number of samples, and n is the number of features. Okay, so this here is 5 transpose, then if 5 is n by n, then 5 transpose is n by n, isn't it? And then you're multiplying this with 5 then, which is n by n. So this here is an n by n matrix. So when you're performing this inverse, you're performing the inverse of an n by n matrix. Now imagine your data set is so large that n is 10 to the 6. You're going to be attempting to perform the inverse of a 10 by 6 rather than million by million matrix. You run into a lot of problems. Not limited to just the size of the number of computations that you need. But what was found again that is known as numerical instability. How many of you have heard of numerical instability? Yes. This is the first one. Many times we're going to hear numerical instability. It's a big problem working with computers because you're dealing with sometimes you're dealing with like big risk problems. The computer has inaccuracy in numbers. You have various representation of numbers. You are like not choosing even the right representation of numbers, variables inside the computer is going to drive into problems. Sometimes you can be dealing with a matrix, for example, as an area that is like 0.0000007, like 0076. So you have a matrix that is full of numbers like this. Opening the inverse of that matrix is so choosing the wrong representation, you need to pass. If you have worked with when you're solving the equation, for example, AX equals to it's a common optimization problem or something like that. You say define x is equals to A inverse P. What exactly do you do? That. If you try running this on MATLAB, for example, you say x, solving the equation x equals to, I think I actually call this inverse of A. When you run this on MATLAB is always going to work. Always going to work. It's guaranteed going to work. Tells you this is a very unstable approach. Very good stability problems. So this does not always work. Because of that, we need to find a more certain way to arrive at the solution. And that's when we now choose to do gradient descent. Gradient descent is basically what I spoke about earlier. In gradient descent, you're gradually moving towards an optimal value as opposed to using an analytical approach to this. So I don't know whether I have this in the slides. Okay. Yeah, I think I've already discussed some of these things.
Reynolds had mentioned this. I say, okay, fine. Inverting an n by m matrix can have numerical instability problems. But something else, sometimes you run into singular matrices. A singular matrix is a matrix that doesn't have elements. For example, imagine I told you to perform the inverse matrix. Always important numerical to works. It's always important. That's not very good. It's not time. It's not time. This is not a singular matrix. This matrix has no impact. So in the case where you have a singular matrix, the analytical approach fails flat. Okay. Yeah. I think these are the things that we already discussed. Yeah. Matrix inversion, in algorithmic terms, matrix inversion is O of M cubed. When you study data structures and algorithms, one of the things that you study is complexity. That is, how does the operation scale as you have more and more? So performing, if your data set is small enough and you end up with an m by m being 3 by 3, that's easy. You can even invert it by hand and end up with a solution. But if you're dealing with a 1000 by 1000 matrix, a million by a million matrix, that's challenging. O of m cubed, it is ridiculously complex. So if m is a million, what is a million cubed? It's 10 to the 18, right? So essentially, the inversion process is going to perform 10 to the 18 operations. We will do that until it starts. Okay. All right. So gradient descent, let's look at that. I mean, there are other cases as well. You can read about this multicollinearity. Multicollinearity means more than one of the columns in the matrix are linearly dependent. If they are linearly dependent, the matrix is going to be singular. I think I've already mentioned singularity. Okay. So the idea in gradient descent is we begin with random weights and then we compute the gradient. The gradient is what we had done before. You remember we had computed the gradient with respect to W, and you sort of know. It's like rolling downhill. You imagine yourself walking down a mountain. And you're hoping to get to the bottom of the mountain or the bottom of the hill. But you have no idea where the bottom is. And it's foggy, it's cloudy, you cannot see your next step. How do you get yourself to the bottom of the hill? You walk slowly still. You walk slowly, you feel the floor, you feel the terrain. If your hope is to get to the bottom of the hill, you don't look for where the hill is going up. You look for where it's going. So you walk slowly looking for the downhill direction until you get to the bottom of the hill. It is the same thing. Now imagine that hill as the error surface. Okay? So the computation of the gradient is really it's like performing that intuitive function of feeling the hill. Am I going down? Am I going up? So you begin with random weights and then you stop, you step opposite to the gradient. The gradient is always positive. The gradient takes you uphill. But your goal is to get to the bottom of the hill. So you compute the gradient and then go in the opposite direction of the hill. Yeah. So you perform something known as a batch update. So you're saying you begin with random weights. Then you compute the gradient. I think you know this symbol here, div. Is it not the gradient? So gradient, this function
with its subscript W simply means you're computing the gradient of the objective function. Remember, we had said this is an objective function with respect to W, and then you multiply it by some small number. You multiply it by some small number. This small number is known as the learning rate. It's a scalar. You multiply it by the learning rate. So in a sense, it's like you're going downhill, and this learning rate is telling you whether do you take big steps downwards or do you take small? Do you take small steps? Because if you're a giant, you might take large steps and end up on the opposite side of the hill, going up again. It's like this. It's always nice to build intuitions. It's like, in a very simple sense, the error happens like that, and you're here. The learning rate says, do you take big steps? And sometimes you may take a very large steps and get on the other side. Then you have to find your way down again. So learning rate helps you to say, take small steps, take small steps, take small steps. At each step, you're asking yourself, am I there yet? If you're not there, you take another step, essentially. But it's a very iterative process, and how slow or how fast it is determined by the learning rate. So you begin with the initial weights, and then subtract the learning rate multiplied by the gradient. Gradient multiplied by the learning rate, and then you update, basically. Yeah, control for step size. Now, sometimes performing, if you look at what was happening here before, is, you're basically computing for how can I put it? You're computing for all values at once. If it's very large, essentially, if your data set is very large, then the convergence, how fast to get to the bottom, is going to take a lot of time. And so we end up with, it's not really, I don't think I explained it correctly. When you say a batch update, really when you're performing this gradient, you're performing this gradient not for all the values, but for a subset of the values. If you have 1,000 samples, you take a small batch, often known as a batch size. You compute the gradient for the objective function for that just small subset of values. That's called batch. We always call it batch gradient descent, or BGD in short. But if, for example, let's assume you have a million samples and your batch size is 20. How many updates will you need to do? It's a million divided by 20. Very many updates, right? And it's going to take a long time. So instead of doing a batch gradient descent is what we do is something known as a stochastic gradient descent, right? A stochastic gradient descent, which is actually much faster than doing a batch gradient descent. So you're making an update based, at a point in time. At every point you make an update. So you end up making fewer steps because you're not waiting for a lot of computations to happen before you make an update. So the comparison is that by comparison, you can just draw a curve here. When you do stochastic gradient descent, it's going to be sort of noisy, It's always going to be, something like that. Something like that. On the other hand, the batch gradient descent is expensive but it's smooth. It's always moving. I think the idea is that with stochastic gradient descent, you might go down and go up, go down and go up, and go down and go up, like that. But with batch gradient descent, you're always going down, not going down. But doing more and more computation, which takes more time. Yeah.
think this idea of gradient descent, will become much clearer when you study like neural networks. So anyway, in general, so we have this linear regression problem. The goal is to solve, in analytical, the goal is to solve directly. With gradient descent, it's iterative tweaks. Okay, taking steps slowly until you get to the bottom of the hill. And the cost as well is smaller. When you take the analytical looks tempting, but for those reasons that you've already stated, sometimes it will fail and sometimes it will take a long time to run because of this complexity issue, O of m cubed versus O of m. If m is equals to n in this case, then it's O of m squared. Right? O of m squared. If you draw the curve of m squared versus n squared, you will notice the difference. M squared will look like that. M cubed looks like this. The moment you scale, you pass the other certain point and it becomes, it makes no sense to take that. And in terms of scaling, with gradient descent, you can have any number of features. You can have any number of features, and you'll always get to the optimal solution. This other one, you'll be lucky to get a solution. The error landscape. If the error landscape is perfectly convex, this is very mathematical language, you're guaranteed to reach the maximum. This is convex. You see this curve over here, it's convex. A convex function has only one global minimum. You're always guaranteed to get to the bottom. Your error surface is not always guaranteed to be convex. Your error surface can look something like this. It can look like this. And you don't know the error surface that you look like. So, when you perform the optimization, you can end up getting to a local minimum. So these are the issues. The thing also with working with gradient descent in most of its variations, like batch gradient descent and stochastic gradient descent, is that because if you're making small steps, nothing you here, and you're making small steps, if you get here and then you make the next step, you realize the next step is taking the error higher. And you take the next step, it's taking the error high, and you take the next step, it's taking the error high, you will be deceived to think that you arrived at the global minimum, whereas in reality, the global minimum is actually there. So there are techniques that you use for making sure that as much as possible you arrive at the global minimum. But anyway, this is what it means to have a convex function. And this is a convex. So the error function is convex, then you always guarantee to reach there. You always guarantee to reach the Okay. There we go. I think that is it. It's super math heavy. But anyway, so every time you run a linear regression problem on scikit-learn, you're always happy to just say model.fit and you get your solution immediately, but you've got no idea
Somebody actually sat down and wrote these things down in the computer program for scikit-learn. It's how you're able to say model.fit, because somebody took the trouble to do this. So I think understanding the underlying math is important. It helps you to appreciate actually what is going on. So what we're going to be learning in the afternoon is actually running these algorithms on a practical problem so that you can see. And hopefully the instructors have actually will show you how you can compute that matrix here. Phi transpose phi inverse multiplied by phi transpose multiplied by y, end up with a solution. Actually show you that this gives you the same solution as simply writing model.fit. Okay. Yeah, I think that is it from me. I don't know, someone has a question maybe. The notes are on the website, all this stuff. Prepare them in a way that I think they are very accessible. Any question? Yes. When to use the
so the question is, do you have to have prior knowledge of your problem being one that can use analytical or?
Yeah, good question. Fortunately, you almost never have to ask yourself that question because there are so many packages out there that have been developed for doing that. Okay, they've been developed already. I think, to the best of my knowledge, when you do model.fit on linear on scikit-learn, it will decide for you whether it will run the analytical approach or use a stochastic gradient descent approach. You never have to ask yourself that question, especially for very basic classical machine learning algorithms like linear regression. You don't have to do it. But out of your own curiosity, if you're curious enough, you can do these things for yourself, and just to be able to, it's like picking under the hood to understand what is going on. Writing the stochastic gradient descent algorithm is actually very easy. It's like 10 lines of code, and you're done. So yeah, you can write this for yourself and see how things run. You can even visualize. Like this point here actually going down. It's a very cool experiment. Just visualize it going down until it arrives at the solution. It's actually how it converges at the bottom. Very interesting experiment for your own benefit. Any other? Okay, I think then that is it. Yeah, we can meet in the afternoon.